So I call this the next step in handheld gaming because we're not at any destination yet. There's still lots of work to do, but this is a significant step forward, and I think it's going to make things better. What we're introducing today is this new form factor, right? We've got a vast gaming catalog. We've got lots of openness in the PC ecosystem, dynamic OEM ecosystem. Everybody's building their own thing, so there's all this vibrance in our ecosystem. We want to take it and channel it towards coming together for some kind of new form factor. Do you know that by 2029 there's going to be more than 1 billion PC gamers? Did you know?
No.
That's a big number, right? 1 billion people. I hear it's big. The other thing that we know is that 34% of PC gamers today have more than one device they game on. So if you got a PC, you might have a console, you might have one of these handheld things. So multi-device gaming is definitely a thing. And that's why we're investing in this sort of like new platform. You know, Intel has done lots of platforms like ATX, Micro ATX, BTX, you name it. Now think of it as handheld as a new platform. There's performance things we got to work on, integration things we got to work on, efficiency we got to work on, and of course software. But that's what we've been doing to get ready for this product. So it's mostly about the GPU when you get to this class. You know that before Damian got here, we had trouble with our GPU. We were okay performance, but when Damian came, there was a huge step. He did the slide, by the way. So there's a huge step when Damian comes. And then, of course, we did the A series. Shalini also joined right around this time here. So we did the Arc Alchemist A series discrete GPU, our first one. And we had lots of struggles, lots of pain. Maybe you guys remember me doing some videos with Damian. It was so much learning through this process. But eventually, the sky dropped XE2 on us. Our engineers kept beavering down in their dark dungeons, and we came up with a brand new IP called XE2. That got put into BattleMage. And BattleMage has been incredibly successful for us. That was a discrete GPU where we took the IP as well and we put it into Lunar Lake. And Lunar Lake has been also a big hit. XE3 was our next step forward, and that's now in Panther Lake. But for a long time, you know, Arc was kind of a mention. We had the Intel Core Ultra with a little nod to the Arc graphics in there, right? Because we're still kind of salt and pepper in the fact that we're a CPU core, and that was Meteor Lake. Eventually went forward to Lunar Lake, and again, Intel Core Ultra 200 series with Arc graphics, again, a little salt and pepper, which is the GPU, but we were, at the time, doing deeper customer relations and better optimizations for power for these handheld devices. But now with G series, this is the Intel Arc G, purpose-built SoCs, deeper ecosystem collaboration and leadership power and performance. What I like is it's our first SoC that is branded Arc. So it's not a Core device, it's not Intel Core something, it's Intel Arc G series. And so that should tell you that this is a GPU-centric device that's going into multiple GPU-heavy markets. Okay, it's the first time we've done that, and you'll see this kind of continue forward over time. Intel Arc G series, it does a bunch of things. It's got PC class performance and flexibility. We are 42% faster than our competition, which is just a gigantic win. We have as much as 11 hours of gameplay with endurance gaming mode, and we support Xbox mode. There's two variants. There's the Intel Arc G3, which is a 10 Xe core variant, and there's Intel Arc G3 Extreme, which is a 12 Xe core variant. So if you think about it, there's a laundry list of technologies that you really need to make this good. Some of it is related to playability, like XeSS. Some of it's related to endurance and like how long can we make this last, battery life. That's things like intelligent bias control and endurance gaming. And I'll walk you through some of these technologies as we go forward. Starting off with, what do we do to the device itself? Well, we optimize core count. This is compared to Panther Lake. So taking a Panther Lake, we've optimized the core count. We've optimized the I/O. We have a new power management strategies, configurable TDP, and deeper co-system engineering with the ecosystem, right? When you think about the SoC itself, we have gone from 4 to 2 on the P cores. So we dropped 2 P cores. We've gone from 4 to 2, 3 to 2 on the display engines, and 4 to 2 on the Thunderbolt. But anyway, we've cut this down and made it fit into our TDP window, and we can actually use a little bit of the fallout coming out of Panther Lake, right? So this is a fantastic device. It's still got the big GPU tiles. So this is 12xe. So you can see that by cutting down on the P cores, we're shifting the ratio much more towards the GPU. On performance, we are 44% faster gen on gen. This is showing you 2x super sampling with 35 watts on the Arc G series compared to 30 watts on the Lunar Lake platform. It's 30 and 35 because that's their peak TDP rating. So when you have both of these devices running at peak TDP, we are 44% faster, and you can see it's across all games. You can kind of normalize that, and you can see, great performance across all the games. Same deal, 44% faster because it's a new architecture, XE3 versus XE2. When you go to 17 watts, we're 24% faster. So as you lower the power envelope, the performance levels get closer, but we're still dramatically faster on the G series compared to Lunar Lake. If you think about us compared to competition, this is the ASUS ROG Xbox Ally X Ryzen AI with AMD Z2 Extreme. That's the name of their device. 35 watts versus 35 watts. Both have both have 2x scaling on, and you can see across all the titles we're about 42% faster. So it's a solid stomping of our competition on that one. I love to see that. If you continue normalizing it, you can see across all the different games, DX9, DX12, DX11, really doesn't matter. Ours is a much newer architecture. They're still on old technology. All right. If you take that performance lead, you can convert it into power. So if you're twice the performance, we can actually go from 35 watts down to 17 watts. So in this case, I'm showing you the G series, the G3 Extreme, running at 17 watts compared to the blah, 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 blah Z2 Extreme running at 35 watts sustained. So we're half the power, but this is telling you that we're approximately the same performance, right? So that gives you roughly double the battery life, which is pretty cool. Okay, so to get all this to work, we have a bunch of software that we had to do. There's software that makes things smoother, there's software that improves endurance, and there's software that does better compatibility. Let me tell you a little bit about it. My favorite, XeSS 3. Okay, now I have had lots of discussions with people. Some people love multi-frame generation, some people hate it. I love it. And I especially love it on this platform, and I'll tell you why. So the way XeSS Multi-Frame Generation works is it rasters a frame here called previous, then it waits a little bit and it rasters a new frame. The rastering at smaller resolutions. Then we use XeSS super sampling to make them bigger. Okay, so we're going to scale these pictures up using AI. Then we put them into this optical flow reprojection AI network. And what we're trying to do there is kind of find matches of pixels from one image to the next pixel so that we can understand how it's moving in three-dimensional space. That way we don't have to actually recolor that pixel. We can just copy it and put it in our new image. So all of that rolled together allows us to generate some very good-looking frames that are the natural frames that fit between these two. Why is that important for handheld? It's because that the energy that this takes is about 1/4 of the energy it takes to raster a frame. So when you're rastering a frame, you got to do a lot of math. You're running shader programs, you're calculating colors for every pixel, you're doing geometry stuff. We don't have to do any of that when we're doing this kind of like this AI frame because we already have rastered frames and we can do kind of a simplified calculation. So that means we get 25% less energy per frame. A way to look at that is if you compare FSR to XeSS, which are both upscaling technologies, on AMD you get 52 frames per second, on us you get 73 frames per second. And our quality is better because XeSS actually does a better, deeper image improvement. This is when we turned on frame gen. So AMD supports 2x frame gen, and they go from 52 to 89. When we turn on our frame gen, we go from 73 to 121. What's important to note is that I don't call these like performance frames. They're all about experience, smoothing frames. And when you start looking at the demos, you can really see as you turn on these generated frames, it makes rotation and translation much more fluid. Another thing to note is we're going from 73 native rastered frames down to about 60 native rendered frames. So our raster rate is actually decreasing as we increase our frame gen count. That continues as we go up. So now we're doing 4x and we're getting 200 frames per second, but our raster rate is down to 50. So it's 73 down to 61 down to 50. Anybody got a guess as to why that's happening? It's pretty cool, right? What's happening is you're trading off some of your horsepower to do this generation. So if you didn't do generation, you get 73. If you do generation, you got to give up 12 frames to do all this generation work. So it's a trade-off between true rasterization and these generated frames. My belief is that the generated frames give you a better experience. Some people don't like it, and they can obviously turn it off. This is just the same data across multiple games. Since we have better frame scaling, better frame generation, we have higher smoothness factors across multiple games. So let's shift gears. We're going to talk about intelligent bias control. This is one of those techniques that we're using to make gameplay smoother. And what's happening here is when we launched Lunar Lake, we found that the CPU was doing its thing and the GPU was doing its thing, and it was kind of fighting against each other. So what GPUs want to do is just stay the same and do the same kind of processing for a long period of time. What CPUs want to do is run really fast and then go to sleep. So like if you're running Word or you're running Excel, your job is to just do compute as quick as you can. So what was happening is when we would run a game, our CPU would spike up and take all the power, and it would slow down the GPU. And then when it finished doing the setup, the GPU would ramp up and take all the power, do its thing, and it would oscillate back and forth. And that was not a good experience. So we added prioritization of GPU frequency, and we added the ability to stabilize the power shifting between the CPU and the GPU. That was all done for Lunar Lake. We did another version of this for Panther Lake, and we added something called E-core first scheduling. Same idea, we want things to be quieter, more quiescent. So this is allowing us to use E-cores before P-cores. It's kind of counterintuitive, but when you use P-cores for processing, it consumes a lot of power, takes that power away from the GPU, and when it comes time to get the GPU throughput, everything is slower. So we're actually better off trying to not use the P-cores. But it wasn't perfect, so we have version 3.5 that's rolling out with the G series, in which we're adding P-core parking. And P-core parking is an ability of us to turn off P-cores entirely when you're at low power levels. So 12 watts and lower? Yeah, so 12 watts and lower, we're just going to disable P-cores entirely because they don't really fit in that power envelope. And it makes the gaming experience smoother. So that's IBC. Let me show you what it looks like. This is before, and before we're kind of like doing that thing where the CPU's running really fast, really power hungry, then it finishes, then the power would shift to the GPU, it would do its thing and it would oscillate back and forth, and it generated a real stuttery kind of frame pattern. When you turn on IBC, the CPU kind of chills out, chill out Winston a little bit, and then the GPU power can stay active. So we're actually able to shift more power to the GPU, which smooths out our frame rate and increases performance. Okay, so IBC is a good tech that helps our delivery with frames when you're shifting back and forth between CPU and GPU. This is a summary of the performance. So when you're at 12 watts, you see uplift ranging from 9% up to 30% depending on the title. This is just IBC on and off. So you can use that technology when you compare to AMD. So again, I'm kind of kicking AMD down a little bit, but it's true. At 1080p gaming with 2x scaling at 12 watts, we are 37% faster. And we're also better quality and we're smoother. So there's lots of goodness when you do a side-by-side comparison. I think we have a side-by-side comparison back here. You can take a look right here. Take a look at it, yeah. All right, endurance gaming is the last big tech. This is a more complicated technology, but what we're trying to do is say, when you're in a handheld environment, you don't need 10,000 frames a second. You don't need 500 frames per second. So we're giving users a controllable setting between 30, 40, and 60. And when they set that down, we will do frame pacing and hardware that's going to slow down frames so you don't get as many generated, you don't get as many on the screen. And we can then use that to use SoC power controls on our die to make everything run slower. and that gives us longer battery life. So by reducing the frames from a user setting, we get longer battery life. Here's what it looks like. This is TF2, and you can see before we're running at 22 watts, and the CPU is just consuming a ton of power because this is actually running at about 250 frames per second for TF2. And the GPU is running at 19% power, but it's just chugging down the battery, right? When we turn on endurance gaming, it drops all the way to 4 watts. And at 4 watts, the CPU is using 13% and the GPU is only using 3%. So everything is quieter, you're still getting enough frames, and Bob's your uncle. Everybody's happy. Okay, you got the user that's saying, I don't need 250 frames, I'm happy with 40. Now this is an example of the power savings. This is Forza Horizon 6 goes from 2.4 or 2 hours and 47 minutes up to 5, almost 6 hours. GTA 5 goes from 2.5 hours up to 6 hours. TF2 goes from 3.25 hours up to almost 12 hours of gameplay. Okay, so that's what endurance gaming does. It's pretty cool technology. It allows longer gaming lifetime by giving up frames per second. A last big tech we did is called precompiled shaders. If you've ever played a game and you get to one of those new levels and it says, please wait, and I'm downloading, I'm compiling shaders. For us, it can take a long time. So what we've done is built an infrastructure where when a new game launches, we actually grab that game and we have people play through it, and they actually compile all the shaders in a lab. And those compiled shaders go up into our Intel cloud that gets connected to by our Intel graphics software. So now all of a sudden, if you have an Intel laptop, our graphics software talks to the cloud and downloads the compiled shaders before you even need them. You have the game installed, you're going to get the shaders. So when you launch your game, it'll use a local copy of the precompiled shaders. It makes the experience of launching a game much, much better. If you look at across a bunch of titles we've already deployed, you can see the savings are everywhere from, say, 30% all the way up to something like 95% or so. And it kind of really depends on how long the shaders take to compile and need them. Now, all this has been going on while we've been engaging the ecosystem more effectively, right? We now have more than 3,000 titles under NDA that we're working with, just game developers. We have more than 1,000 titles that we've released as we've engaged. So our dev tech and devrel teams are active. More than 200 day zero drivers. That's like we did a driver optimized for a specific game and it was available on the day that it launched. But what I'm super excited about is more than 400 games now implement XeSS, and more than 100 games implement XeSS with multi-frame generation. It's pretty cool. I don't know if you remember, but when we launched XeSS, I got on stage and I had a slide with like 5 games, and I was like, look, XeSS is in games, all 5. And I was like, yeah, and everybody's like, quiet claps. But now, hundreds of games. So we're kind of over that hump of, getting into the ecosystem. Our technology is now widely deployed. Okay, so with that, summarizing, we are 44% faster than our prior generation. We're 42% faster than our nearest competition. We have all these cool frame gen technologies that make gaming smoother, and we have intelligent bias controls that balances between the CPU and GPU more elegantly and gives you smoother gameplay.